Well, hello everyone, and welcome back to the prep for Inferential 1, hypothesis testing, Z and T. So let's look at some Z and T questions. In fact, I'll zoom in a little bit so we can make the questions bigger. So quality control department wants to periodically test the quantity of their packages. They want to verify packages being filled to an advertised quantity, which is 250. They take a sample of 30 boxes, determine if they are over or underfilled. They find that 30 boxes have an average number of 251 paper clips, a standard deviation of 0.8. So what test should it be? All right, now this one is going to surprise you, maybe, but this is a t-test. You might be saying, well, wait a second, but they have the standard deviation. Well, they do, but that's of the sample. They do not have the standard deviation of the population. So the sample standard deviation is going to be a stand-in for the population one when we run the test, but that makes it a t-test. And the direction of the test is two-tailed since we don't know which direction, over or underfilled. Okay, Kroger knows that historically the average customer spends $52.53, standard deviation of 28.29. So now we have the standard deviation, so we know right away that's a Z. Okay. Pickup orders to be more expensive. So they're looking to see if it's more expensive. More means right tail test. And advertisements, new print ad. Okay, so we know the standard deviation, so it's Z by definition. New ad's different. Just different means that it's two-tailed. And last one, was 63. Okay, so they have a standard deviation, but it's for the sample. So they don't have the population, so it's a t-test. And they want to see if it's faster. Now, faster, you're thinking faster means more, but it doesn't. Faster means less time. So it's one tail left. And that takes care of these. So let's keep going. Okay. So a popular student cafe on campus advertises that their large cold brew coffee cups are filled to exactly 20 ounces. To ensure consistency and fairness, the cafe's management wants to make sure the filling process is accurate. If they underfill, students are shortchanged. If they overfill, the cafe loses profits. Due to slight variation in the pouring machine, they take random samples of filled cups to check the average fill. The quality control team collected a sample of 25 cold brews to investigate whether the average differs from the advertised 20 ounce. The data is shown below. Conduct the appropriate hypothesis test at 5% to determine whether the current mean fill differs from 20. All right, so you don't see standard deviation anywhere in this. So this is going to make this a t-test. As a t-distribution, so it's going to be t instead of normal mu 0 or mu naught. It's going to be t. All right, so we have the population mean is what's advertised, and then the sample is the sample. Same population mean is the null hypothesis, and we don't know if we're over or under, so we're just looking to see if it's different, which makes it a two-tailed test. Oops. I'd actually pick two-tailed. There we go. All right, so now we got some numbers to fill in, and we have some of these numbers. The advertised is 20. The sample, well, let's see what it is. And the sample size. All right. So now we are going to use the standard deviation, but not the population one. It's the sample standard deviation, which we just called S, and we're actually going to have to compute it because it's not in the problem. And that's standard deviation dot S, not this. So it's going to serve as a stand-in for the standard deviation of the population, but that's what forces us to a t-distribution, which is slightly less accurate, but still pretty good. All right, so the standard error is going to be that divided by square root of n. That little thing doesn't change. Alpha is 5%. Okay, is the critical value of x bar. It's a t-score this time, not a z-score. Probability of x bar. So we're going to cut the probability in half to get the two sides of the distribution, since we don't know over or under filled, so it could be either way. And the t-score. All right, so we're going to have to start using some of these calculations here. So we're going from p of x bar to x bar. So the t-score is t dot inverse equals t dot inverse for the left side, the probability, and then, oh, degrees of freedom. Well, that's new. So degrees of freedom in a t-test, one sample t-test, is going to be the sample size minus 1. And then for the opposite side, do the same t dot inverse, but this time it's 1 minus, because it's looking right. 1 minus that probability, but the same degrees of freedom. So sample size minus 1. And then we calculate the raw values the same way we did before. T-squared times the standard error. So that gives us how far we are away from the mean, but then we actually have to add the mean to that to plot it. And there we are. Except I did it wrong. So let's see what I did wrong. Let's see. T-score times the standard error. Oh, it's not the sample mean that we're adding it to, because we're trying to see if we're different from the population mean. So that's our reference point, because this is the advertised distribution that we're plotting on. There we go. And then for this one, it's going to be the t-score times the standard error. Again, plus the population mean, not the sample mean. All right. And then our sample, x bar, is this guy. And the t-score is equal to x bar minus mu divided by standard error. Okay, and the probability, well, if it's way out here, this is definitely not going to be a reject. So, but let's calculate the probability anyway. So it's probability, but looking left, right? So this is from x bar to p of x bar, so we're on this side, x bar to p of x bar. We're looking for probability looking left, which is going to be t dot dist. So equals t dot dist of that. X is the t-squared. It's a little weird, right? But it should be t probably, whatever. Degrees of freedom is the sample size minus 1. And then it is a cumulative distribution. So 31% probability, which is a whole lot higher than 2.5. All right, so when we construct the confidence interval around this x bar, for sure it's going to cross the mean of the advertised population, which means there's yet another reason that we reject the null, but let's do it anyway. So we're going to do, now, again, we can cheat, right? Because we've got the right hand of the two tails. We could grab this 2.06, but if that's going to freak you out, then just, you can go ahead and calculate it again. So t dot inverse 1 minus alpha divided by 2 actually, that's not the alpha divided by 2. Be that alpha divided by 2, and then that minus 1 for degrees of freedom. But I shouldn't have ended the parentheses there. Let's go back. There. Over 2. Oh, I'm going to multiply that by the standard error. Times the standard error. All right, now, could have gotten it much faster if we just done this. Look, we've already gotten this number, so that's the right hand, times standard error. Get the same thing. And conceptually, I kind of like this better because it's not just memorizing a formula, you're actually understanding, oh, it's the t-score for a two-tailed distribution, the positive t-score, times the standard error. That's going to give us our margin either side of our sample. So let's grab our sample. So that equals that minus margin of error. And on this side, it's that guy plus margin of error. And sure enough, that crosses the population mean for advertised, so there's no way we're rejecting the null hypothesis. But let's go through the motions here anyway. So our probability that we're checking against on each tail is 2.5. The p-value is that, which is a whole lot more than alpha, which means that we are going to fail to reject. And then we have two critical values. Okay, and this is the lower one, and this is the upper one, and the test statistic is that one. And using this approach, our test statistic is well within these two critical values. So it's failed to reject region. And we failed to reject the null. So we have to simply say there's not a significant difference between sample and advertised, which means that those populations could be the same, could be equal. And if you reject the null, we say it's statistically not significant. All right, now this is the problem that looks for us to give the standard error. It's there. Empirical rule to get 95% confidence be from here to here, so 1997 to 2003. Oh, it's actually a drop down. There we go. And what raw value is the lower cutoff for rejecting the null? It's a raw value. This guy. And our sample mean is this guy. And what are we estimating the confidence interval? The population that would correspond to that sample. And what population might that sample have come from? That's what we're estimating. And the interpretation is that we're 95% confident that the population mean for samples between 1996 and 2002. Where are we getting that? There's the 1996, there's the 2002. And it's also here, 1996 and 2002, on the two ends of that green line. So we're all good. And I'll end this video here and then we'll start a new one.